Thanks, Mark. I'm probably going to disappoint now. So, yeah, let the pro do it. Yeah, so don't keep your expectations that high. So, but this is a talk that is going to be kind of wide ranging, and some of the stuff's pretty mature, and some I think is in progress. But I thought it'd be fun to get. Oh, okay. I was told this mic would work, but maybe not. So, okay, yeah. So let me get the pointer going, and
yeah, this mic isn't very sensitive. In fact, I'm going to move it over here if that works.
Okay, sure. So you can see the highfalutin title of this talk, but really what we're going to be looking at is the Paleozoic Orogenies around North America, and we're going to be looking at it from the basin back into the mountain belt, because I think I'm a stratigrapher.
This might need to actually hold the mic.
Oh boy, this is going to be a test of
I apologize.
how is that? Okay, I've never been accused of being soft-spoken, so this is weird. Anyway, so that's kind of the theme here. So without further ado, I have a lot of slides, and so I'll apologize up front about the denseness of the talk. So the objective here is to evaluate the timing and magnitude of these mountain building events on the margins of North America. And we'll look at 3 margins in total. And so the context for this is that the problem with these ancient systems is that ongoing deformation and erosion of the fold thrust belts obscures much of the primary evidence. Things like, basically being able to do reconstructions, looking for structural growth strata, et cetera. And that's especially true in these ancient multi-phase systems. But the opportunity here is that the linked sedimentary basin, in other words, the foreland, generally contains a much more complete preserved record of the response to mountain building. So it's kind of an indirect way to looking back into the mountain belt. So the approach here is we're going to look at the detailed history of flexural subsidence via what I would call high-resolution geohistory analysis. In other words, a series of some 85 1D calibrated basin models that are tied closely to stratigraphy and estimates of bathymetry and elevation. We're going to restore missing section that has been eroded by integrating stratigraphic extrapolation, in other words, isopac projections with basin modeling. And we're going to quantify the load and the topographic uplift by 2D modeling of the flexural effects based on the stratigraphy. And we'll also evaluate other stratigraphic indicators of the flexural effects, such as these clastic basin margin wedges, steep margins, turbidite systems, subaqueous evaporites, and especially organic rich source rocks that are related to the development of these steeper margins. So there's a bunch of people to acknowledge. I'd like to highlight Maggie Curry at NC State and Trey Sessoms, who recently graduated from U of H, who worked on portions of the Appalachian part of this talk. So here's some excuses. It's a work in progress. I think the Appalachian stuff's pretty mature. We have a paper in preparation, but some of it is much more kind of out there at the bleeding edge. I'm sure there are people in this room.
I have a really hard time in the back. If you can hold it a little bit closer to your mouth.
Okay, sorry.
Is that better, guys?
Yeah, I really don't like hearing my own voice, but okay. I'm sure there are people in this room who know more about some of these basins than I do, and it's really hard to know. So I'm actually interested in comments and questions afterwards. And of course, there's a ton of publications on this that we've leveraged along with, I think, some significant new work. So the themes here is that inferences of plate geometries and trajectories can be inferred from the spatial and timing and magnitude of the basin response. So it's not just subsidence, but it's also paleogeography. And some of these plate scale kinematic linkages are indicated by coeval timing at a continent scale. So we'll talk about things such as sag basins, ancestral Rocky Mountains, et cetera. Another kind of challenge here is that the upper Pennsylvanian and Permian 4D sediments of the whole Appalachia-Ouachita system have been mostly eroded in their most proximal portions in the thickest part of the 4D. So reconstructing them has been a challenge, but I think it's important to understand kind of the end state of these systems. And so we're also going to see common ties of subsidence events to source rocks, to thick basal evaporites, and to some of these clastic basin margin wedges. And I'm not going to have time to go through all of these, but I'll show examples of each. So this is kind of the playground, if you will, largely focused on the lower 48, but we went up as far as the northern BC, the Liard, Hudson's Bay, and I'm not going to talk about the Maritimes or the Variscan system in Europe, which you've also tied in, but we're going to go through these four elements. About a little more than half the talk is on the Appalachian system here on the present-day eastern margin of Laurentia. Then we're going to kind of continue that transect through the Ouachita Marathon Belt. We'll talk about the ancestral Rocky Mountains, which should be near and dear to the heart of people here. And then we'll follow up with a short treatise on the antler orogeny here on the western margin. And so on this map, what you see, you'll see different versions of this arc coverage, but the red line is the last deformation front for these thin-skinned systems here and here. And then the gray outlines are the basin outlines for Paleozoic basins. And this is, I just took this straight from the USGS, not to be too interpretive. And then the red or pink are the basement uplifts associated mostly with this arm system here. Sutures are shown in purple for the Appalachian system. We'll talk more about that. And then the 85 basin models are shown as the red dots, not including the ones over in Europe. So I'm just going to introduce this chart. I'll show it again later on, but this is a plot of just a kind of a bar and whisker, qualitative bar and whisker of geologic time on the vertical axis versus all of these basins and sub-basins. And they're, obviously it's a two-dimensional view of the map world here, but they're kind of range roughly from the east to the west here. And so first we're going to talk about the Appalachian system in some detail. And we're looking at superposition of four orogenic events here. And that's why we see this stack on stack on stack. So obviously a multi-phase system, long-lived from Ordovician to Permian. But what we'll talk about in more detail is the variability in timing on the onset of these events, these flexural events, and also the magnitude, how that changes spatially along strike. And then most of the rest of the talk is going to be on all of these Pennsylvanian Permian systems, which includes the Ouachita Marathon system, the arm basins here shown in green, and then we'll end the talk with just a couple of slides on the antler orogeny here. So one last thing to mention on this is you see this line here with the hatchering on top. That is all section that's been eroded. So you get the onset can be recorded quite accurately in the preserved stratigraphy. But knowing when this stuff ends, when the record has been removed, is obviously a huge challenge. And we've attempted to do this through calibrated basin models to tie in the vitrinite reflectance, and also try to use the trends of subsidence and isopactics that we've seen. But you need to be aware of that uncertainty, which is significant. So let's start with the Appalachian system. So this cartoon is, I adapted it from something at Scripps, but it's a depiction of what happens through these four orogenies in the Paleozoic. So the first orogeny that you may have heard about is the Taconic, and it's basically this volcanic arc that closed the Western Iapetus Ocean and collided with North America, with Laurentia, starting in the Middle Ordovician. So this is the first collisional event that follows this kind of late Proterozoic Cambrian passive margin and rifting event. Following that, you may have not heard this one. It's kind of not much advertised in the literature. Is the Selenic, which is a short duration but high magnitude event in the late Silurian. And it involves a microcontinental plate called Gandaria, in which some of the terrains have been identified, obviously up in the Maritimes down through Connecticut. And it seems to have had an associated arc and back arc system, but was a microcontinental plate that got welded on in the Silurian. And then next we have Avalonia, which is Northern Europe, and attached to that was a microplate called Baltica. And so that's basically Northern Europe. It's the British Isles, Scandinavia. They joined at the Caledonian orogeny, which you've probably heard about. And that basically closes the Iapetus Ocean and collides with Laurentia in the middle Devonian to late Devonian. And that's a very large event and pretty well kind of known in the literature. And then finally, we have the culmination of all this, which is the Alleghanian event called the Variscan, or sometimes the Hercynian in Europe, because it continues through, that margin continues through Northern Europe. And that's the docking of Gondwana, which is, you know, in total is Africa, South America, Yucatan, and actually parts of South Europe. And that collides in the Pennsylvania Permian time. And when you have these two sutures developed associated with those last two collisions, the Riic or Sewanee associated with the Gondwana collision, and the Iapetus associated with the Avalonian or Acadian. So that's the background. This is kind of the database, if you will. We have 11 stratigraphic cross sections, over 100 wells. 7 were reconstructions of 4 high-quality USGS sections, and 7 new ones, including this long strike section that I'll show you from New York down to Tennessee. There's 12 calibrated basin models, plus another 8 from USGS. And then we have these flexural profiles, on which we have 17 different flexural wedges defined stratigraphically on these 5 transects. What you see on this map again is the deformation front at the end of the Alleghanian. That's the valley and ridge. And then the forelands out here. The forebulge is not well preserved because of erosion, but it would be in the vicinity of the Cincinnati Arch Nashville Dome. And then the brown line is the demarcation between the folded Paleozoic sediments and the metamorphic igneous core that's been exposed that involve a lot of these terrains, arcs, especially in the Devonian, that were sutured on. So next slide is going to be one of these USGS sections, just to illustrate the gross stratigraphy. So this is a profile from southeast to northwest, about 250 kilometers. Just grossly what you see is this Fulton Thrust Belt, the valley and ridge, is a very lightly deformed Cumberland Plateau. You know, realize that this is a 100x vertical exaggeration. Sorry for my structure friends out there. And then you see this wedge of these forelands, very broad forelands, a very strong crust here, consistent with current estimates of lithospheric strength. And the 4 orogenies we're talking about are here, but this whole system starts with a rift and sag phase in the Cambrian and lowermost Ordovician. This is the Rome Trough. And then what we see is these wedges in the Taconic, the Salinic, the Acadian, and then as you see, as I mentioned, the Alleghanian has only kind of a scum of stuff preserved, mostly in the lower Pennsylvanian. So next slide is going to illustrate a 1D basin model from this, and we're going to be looking at if there's a correlation between these 4 defined orogenic events and any kind of subsidence signal. And it would be a short talk if there wasn't. So this is from West Virginia. It's in the 4 deep, and what you see is this is of course subsea depth. This is from Petromod, geologic time on this axis. And you see 1, 2, 3, 4, 5 rapid subsidence events, and then periods of very low subsidence in between. And so in brief, we're seeing the rift, post-rift sag in the Cambrian. We're seeing this middle to upper Ordovician Taconic event, seeing the upper Silurian short duration event, the Salinic, the Acadian, shown in green here. And then we're seeing the late Alleghanian occurring mostly in the Virgilian, the latest Pennsylvanian through Permian. So all 4 orogenies can be recognized by this increase in subsidence rate, and we've interpreted this and can easily model it as flexural effect. And consistent with a flexural load origin, as you'll see, the magnitude of subsidence is highest in the proximal 4 deep, and is obviously as you come out onto the forebulge, it's very low. There's limited flexural subsidence associated with this earliest phase of the Alleghanian orogeny in the late Mississippi and early Pennsylvania in this particular area. And so we're going to look at other things to relate basin response to orogenesis, as you'll see in the next section on paleogeography, lithofacies, isocores, and flexural models. So let's take a look further north and further south. This is up in Pennsylvania. This is the North Appalachian Foreland, and right on schedule, you see these 4 events. The Selenic is much larger here. It's the Acadian and the late Alleghenian, mostly a latest Pennsylvania to Permian event. No signal at all for a Mississippi and most of the Pennsylvanian here. You go down to the Southern Appalachian region, this is in Kentucky, and you see a very large subsidence increase in the late miss. And so this is occurring by Chester time and continued, I lost my pointer. Oh, there it is back. You see this basically continue into the late Alleghenian. So we're seeing some changes along strike here in the system that we would invoke to changes in the location of mountain building during these different periods. And so no Selenic and Acadian event in the Southern Appalachians, and no early Alleghenian, which is coincident with the Ouachita event in the Northern Appalachians. And here's a cross-section. This is this cross-section from New York to Tennessee, and just sort of more visually shows what, you know, the highfalutin Petromod model show. It's really thick out here. These three orogenies, Taconic, Selenic, Acadian, and basically the Selenic and Acadian, that section is virtually absent to the south. So there's no accommodation in the southern area for these this Silurian and this middle to upper Devonian event. The Taconic continues to the south, so there still seems to be a signal, but it's significantly thinner. So there you see the interpreted distribution of these orogenic events based on the sedimentary response. And one thing that kind of put this in perspective, we can look at the geologic time involved in that. And if you take the 3 colored intervals versus the uncolored intervals, which are these sort of inter-orogenic periods when there's not a lot going on, there's as much time represented in these white intervals as there are in the sum of these colored intervals. So there's huge changes in flexural accommodation. And we tried to integrate bathymetry, and they're all decompacted and all that kind of business too. So let's talk about flexural modeling. So, you know, this is the big boy at the end of the diving board kind of deal, right? So the stronger the diving board, the longer the wavelength is. You got one that's a wet noodle, and it's just going to go like that. So that's a weak coupled lithosphere. So that controls the wavelength of this 4 deep to 4 bulge transition. The size of the load, in other words, how big the boy is at the end of the diving board, controls the amplitude along with the flexural rigidity. Because if you've got, say, a 100-pound person at the end of this diving board, and it's a really strong board, it won't deflect as much, but the area that it's encompassing is still quite large. And you've got a weak one, that 100-pound boy, it's narrow, but it's a shorter wavelength. So those are the factors that control the shape of this stratigraphic profile. So each of these yellow points is a stratigraphic control point in sum, and that could be from a cross section, could be from an isopac, could be from a seismic line. And so what we can do is we can come up with estimates of the strength, the flexural rigidity here from the shape of this, and we can also come up with estimates of the load. So how do we do this? Well, this is a real elegant code, MATLAB code that was written by a U of H PhD candidate, Kurt Sundell, and his supervisor, Joel Saylor, who I worked with on this. And basically, it's a real elegant solution. You put in the stratigraphy with the accepted error bars, and that's the little tiny dots you may not be able to see. And so that's the accepted variance for fitting that curve. And this is a Monte Carlo simulation. We usually run about 100,000 trials. And you don't have to specify the strength of the crust. You don't have to specify the height of the load. You don't have to specify the width of the load. It'll just randomly select those parameters and only allow the ones to pass that fit the error criteria. So it's very agnostic. You have to make very little assumptions on this. And I think that's what's elegant. And then you get reported out the mean and the standard deviation of all these parameters. So this is a real example from the Appalachians. The only other thing that I'll say that we have done is we do say that these are all right tapered, like a fault belt would be. And we also make sure that it doesn't exceed a reasonable critical taper on this. And we also have to define the pinpoint. I'll show you how we do that after that. So we get estimates of the load height, the topographic relief, the width, and the flexural rigidity from this technique. And I don't have time to go through all of these, so I'm just going to cut to the chase, just show you the topo relief. So let's start with the tectonic orogeny. This is that kind of zoomed in map. These are the 4D deposits in the middle and ordovician that represents kind of the stuff that was being shed off of the growing mountain belt. We've restored the deformation front to this place here, and that's where we pin the flexural load. I can tell you offline how we did that. And what we're going to do is look at the resulting isochore of the fill in the foreland that results. And so it's really hard back in the fold belt. A lot of this stuff's not preserved, but we do have it out here clear of the last deformation front in the valley and ridge. And you see that we've got this thick up to about 0.8 kilometers of tectonic foreland deposits preserved here. And of course, that's thinning up towards the hinge of the fore bulge, but it's also thinning to the south. So we're seeing that it's a larger magnitude event up to the north. Interestingly, if we look at the Utica, which is deposited at the onset of this subsidence event, it's restricted to that same isopac thick. We don't have enough control to investigate this yet, but I'd like to follow up on that. And the Utica basically becomes absent to the south. So the Utica, you probably heard about it, it's a major shale gas play. It's a big source rock, and it occurs right at the onset of this tectonic subsidence. Moreover, the Martinsburg Fleesh, which is a carbonate-prone turbidite system, is restricted to only the northern part of this area. So we've got the biggest flexural effect here, the isopac thick, the deposition of the source rock, and also the deposition of this carbonate clastic sediment gravity deposits, all restricted to the north. And then we can come up with estimates of what the topographic height of these mountains were. And we see we get up to about 3.5 kilometers of relief. So these are pretty tall mountains. Now we could have a long discussion again about the dynamics of this because that's a little misleading, but on a sort of a semi-quantitative basis, you see that decreasing to the south to about 1 kilometer when you look at this transect through North Carolina and Tennessee. So what about this relationship between source rock and these flexural events? This is a cross-section from Edmondson, 2019, and it basically is a dip cross-section. It shows the, here's the initial rifting phase, sag, very carbonate-prone, Knox unconformity, and then we have the Utica deposited there, and then the also famous Marcellus deposited in the middle Devonian here. And if we look at these subsidence events and orogenic events, see the Utica occurs right at the onset of the tectonic. We have this evaporite-prone selenic that I'll talk about next. And then the Marcellus occurs at the onset of the Acadian orogeny. And then what is interesting for this Devonian kind of wedge is that there's a rolling outboard of these other source rocks that you also may have heard of, the Rhine Street, the Huron, and the Ohio shales, that are progressively young and pushed out at kind of the toe of the slope position as we fill this in with this Catskill Delta. So let's just kind of, to beat a dead horse, sorry for any horse lovers out there, but here's a whole bunch of, both from the central Appalachians and the northern Appalachians, a bunch of basically geohistories, subsidence curves. And so you see this tectonic event, and the Utica is spot on at that nick point of the onset of subsidence. And then we see the selenic, we'll talk about that next. And here is the onset of the Acadian event. These are the four deep ones here. And you see that's right when the Marcellus is deposited. And then here's the younger Rhine Street, Huron, Ohio shale ones as well. So I'm just going to present kind of a very kind of general model of this. This actually, I think, is a not sole motif for source rocks by any long stretch of the imagination, but I think it's a common motif that the subsidence events, including in sag basins and rift basins, the onset can often coincide with the deposition of important petroleum source rocks. So here's a schematic. It shows the fold belt, wedge top sedimentation here, the flexure. So this is going up, this is going down. And what I would posit is that we get the deposition of these source rocks especially prone to occur at the initiation of this flexure. And then we get progressive infilling with a wedge of material that can be very variable. As you saw for the Acadian, it's a clastic wedge, a deltaic system. And then these source rocks can kind of roll outboard as the location for favorable deposition kind of moves away from the 4 deep, which is now filling in. So there's a number of factors that could be positive for this. That's this initial accommodation. Basically, the load is almost instantaneous. The bottom drops out, and it takes a while for the sedimentary engine to kind of get going and fill in that space. So the first thing that happens is potential for a condensed section, basically a second order retrograde related to subsidence. And then with this increased relief from the orogenic belt into the basin, there's going to be a steeper margin. You know, some of you have seen some of the seismic lines from, say, Pennsylvania. You do see these low angle cliniforms associated with the Marcellus system. And so there's an opportunity for upwelling. You also have potential introduction of nutrients from runoff from the rising hinterland, so that could help productivity. Sort of a more wild idea, but I've seen it possible in several places, is the arc volcanism associated with this is also going to introduce nutrients into the system. And Devonian has a big arc associated with it. That's very well known from the outcrops. And then finally, by virtue of the geometry of this system, there's going to be an opportunity for silling and restriction, so you can get dysoxia. This doesn't happen all the time. Maybe all the factors don't work, but I think it does favor deposition of source rocks. So let's talk about the selenic briefly. This is a short-lived event. It's an isochore up to about 0.8 kilometers, located to the north. And now let's look at the fill. This is a very evaporitic system. Others have proposed, and I like this model, is that the aridity is enhanced by an orographic effect. And so we get the deposition of these thick halites of the salina group. This is a isochore of net halite. You see up to about 300 meters of halite here. And that terminates to the south. And that's similar to what happened to the total isochore of the interval. Interestingly, we have thick coeval halite in the Michigan Basin to the northwest. And the halite pinches out going across the Cincinnati Arch both ways. So here we see a different kind of sedimentary fill pattern with these evaporites. See the much lower system here because it's short-lived, about 1.5 kilometers total height from the flexural effect that we've seen. So we're going to even take this further and say that by virtue of only seeing basically the sedimentary response to this collisional event here to the north, that we can infer the southeast end of the Gandaria microplate. And this is really hard to do in these rocks as they are, because these terrains have been beat up. So it's a very indirect way of going there that I think, you know, has some merit, and we want to follow up on that with a geodynamics expert. So now let's talk about the Michigan Basin. So that's Michigan's kind of classic sag basin, right? So it's got, you know, F-all for structure in it. Just a big bowl going down. Well, it's not a uniform bowl going down at a constant rate. It shows these same 3 Paleozoic events that we talked about in the North Appalachian Basin, the tectonic, the selenic, and the Acadian event. So I think there's strong circumstantial evidence that there's a kinematic linkage between the Michigan Basin, and also we see this in Hudson's Bay and the Illinois Basin, and the Appalachian system. So it's kind of a far field linkage, whether there's inherited crestal weaknesses there and it's buckling. I'd like that. I'm sort of looking for that, but I haven't seen evidence yet, but you know, that's the correspondence that we see. So the Acadian is a really big mamoon here. This is the outcrops of the Devonian 4 deep deposits. This is the Marcellus outcrop. And this is the suture that was associated with the docking of Northern Europe, Avalonia. Again, here's an isochore up to 2 kilometers of thickness here. And you see that's restricted again to the north and decreasing to the south. And again, we see that the major source rock here, the Marcellus, these are published isocores for Marcellus Shale, and they're located pretty much in the same place. And so this is another example potentially of this source enhancement associated with the initiation of orogenesis and the flexural relief that's developed. And then the latest Devonian, so this eventually fills in, as I showed John Edmondson's cross-section, with a clastic wedge, and that is this informally called this famous Catskill Delta. So this is from Trey's work, and it shows, based on both published outcrop and about 100 well-logged interpretations, it shows this pattern of filling in the basin with this up-dip non-marine section through a shoreline system, all the way out through the Ohio Shale, which is still a very rich source rock in the dispositions. And again, it's located in the same position. So even without this flexural models and these geohistories, you would kind of suspect something's different going on along strike. Is that there's a lot of basin heterogeneity, and that the real action is in the north and central Appalachians. And again, we would put the southeast end of Avalonia basically as reflected through the paleogeography and the flexural effects right at this position here. And then we come to the big problem, and that is we've got this big Alleghenian event, but not that much preserved. And this kind of shows the guts of it. The blue is a Pennsylvanian outcrop, so we have incomplete Pennsylvanian section there. And the purple is Permian outcrops. This is just basal wolf camp. We got up to about a quarter kilometer of preserved lower wolf camp in the Dunkard group right here. But how much more section was here? How can you try and reconstruct that? Well, we have the beauty of having a 1900 surface vitrinite measurements from the USGS of Pennsylvania and Permian and Mississippian coals. And so this allows us to see how much burial was there by virtue of modeling this. And we're talking these rocks have been hit pretty hard, 0.6 to 1.4 RO at the surface. And this is very good vitrinite data because it's from coal, mineable coals in many cases. And you see that's getting, you know, higher as we go into the later 4D. So basin model here, you can, you know, basically model what the result is, tie the temperatures in the wells and blah, 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 and all that stuff. If you don't put any exhumation here, you're about 1 RO unit too low in maturity. And these surface ones are really important because they're very reliable. Some of the ditch sample stuff, you know, you kind of worry about, is it real vitrinite, et cetera, where they come from. So we've taken this approach and we've reconstructed the Pennsylvania and Permian. This is how much we think it's been exhumed, up to about 4 kilometers exhumation. These are published thermochron points. We have one that's out in the basin, so it's where we saw in excess of 4 kilometers independently from basin modeling, and from Fission Track, they saw 4.4 kilometers of exhumation. So we think this is, you know, directionally pretty good. And then as an example, you can say, I can make it a isocore, no, I'm not on drugs, from section that's mostly not there by reconstructing it with the basin models. And it's got a very kind of reasonable foreland basin kind of geometry to it. So why is this important besides sort of understanding scientifically what this Alleghenian system is? This burial makes the Marcellus mature. It would barely be in the oil window over most of its area. So it basically, this was important on a purely commercial basis. And it's also a big deal for the Utica because Utica sits out here under less burial. So you need that extra kilometer or so even in those distal positions. So let's, yeah, I know this is long. So let's continue through the Ouachita-Valverde system. And these are often treated as separate from the Appalachians, but I think I could show you a continuum of this. This is the Black Warrior. Here we see the onset of the basin in the Chester in the Mississippian age and continues up. And again, we've got erosion at the surface and under the base, upper Cretaceous unconformity, so we got to reconstruct that stuff. But it's basically mostly a non-marine to coastal fill with a lot of coal measures in it. And we can take the Black Warrior. It's got very similar timing in southern Appalachians where we saw that early Alleghenian event, which also started in Mississippian. So the Black Warrior looks like a continuation of the southern Appalachians that we saw in Kentucky and Tennessee. take it to the Arcoma, and the Arcoma is younger. It doesn't really start going until the Moro token time. So very different in terms of timing. And then we get more Permian subsidence in the Arcoma than we see in the Black Warrior, so it continues subsiding later. This is what the Arcoma looks like. So we see a big wedge now of deeper water, including these submarine fans in the Moro and Atoka. And again, we've had to reconstruct the section because we've got 0.8 to 2 RO at the surface. And so we get the same kind of wedge, but totally different timing than the Black Warrior. And then you go to Valverde. I skipped over Fort Worth, it's intermediate, but we'll look at this curve there. Same kind of wedge that we see in a process in the, get a flooding, on top of the Strawn, and you really get, it's Virgilian to Wolfcamp in age is when this flexural wedge is. And again, we've had to restore it for the Leonard and Guadalupean here, but here the subsidence is really initiating in late Pennsylvanian time instead. So we've gone from onset in the late Mississippian to onset in the late Pennsylvanian, 20 million years later. So that, you can't kind of average through these things. And here's, there's the Fort Worth, there's the Valverde. You see it younging again from the Fort Worth Basin to the Valverde. So here's kind of a summary of this whole system in terms of the onset of the timing. You see it on these curves. Is we see it oldest onset in the late Mississippian, in the Southern Appalachians, in the Black Warrior, and younging to the north, and younging also to the west, into the Marathon region and into the Northern Appalachians. So I'm going to kind of, arm wave a little bit here, or maybe a lot. This is potentially an indenter. That may have been the first place that Gondwana made contact with Laurentia. And so we've already seen where the Gandaria and Avalonian plate would be inferred from the flexural effects in the Silurian and Devonian. Now we would see Gondwana coming in. Here's the different elements that split apart later. That's another story there, but for another day. And basically it hits here first and then kind of rolls outward in both directions. And it kind of fits the geometry in a way. And this has a very kind of profound influence on the basin fills, this variation along strike and timing. And this is actually exactly opposite what Dickinson published 20 years ago that I still can't figure out. I've talked to Ryan Leary about that. He doesn't understand either. So briefly, ancestral Rocky Mountains. To me, it's kind of like a underfilled Paleozoic version of the Laramide in a gross sense. You've got these cattywampus uplifts and basins. They're all different orientations. Each basin is kind of its own experiment. And their uplifts are going up while the basins are going down. So I'm going to start where we can more closely relate the fold belt to the one of these arm basins. That's the Permian Basin here. Oh yeah, back to this, sorry. So we saw younging here, the decrease in these, and now we're going to look at these arm basins. And you see that they vary in timing from Mississippian onset to latest Pennsylvanian. Again, so we're seeing the same kind of diachronaity. Again, Valverde, much younger than the rest of the Ouachita systems, which are younging towards the Valverde. If we look at the Valverde versus the Permian Basin, and unfortunately I should have made the same color, it's this curve right here. It's right on schedule with the Delaware and the Midland Basins. They start at the same time. So the timing is identical for these. It's not the same mode of subsidence. They're not directly related in that this isn't just one simple foreland, as everybody would know. And then the other thing that's interesting is you see that this is a Central Basin platform. This is at the plunging end of the Central Basin platform. They're subsiding at a low rate or uplifting while the basins are going down. So this first phase is a differentiation of the basin with the Diablo platform, Northwest Shelf, Central Basin platform, and the Delaware Midland basins as well. And then this subsidence following that has pretty uniform subsidence rates through the rest of the Permian. So this is a Virgilian Wolfcamp phenomenon, and then this is a basically something where the platforms and the basins are going down. They're staying differentiated because of carbonate nucleation on the highs. So there's still platform to basin relief that's exceptionally large, but you're piling up a lot of section of Leonard through Ochoan age on the highs. And a big nick point on this is this lower Wolfcamp unconformity. So we talked about that already. Now I'm going to show this ancient West Texas Geological Society cross-section, which I like for the geometries. Here's the lower Wolfcamp. You see it truncating. That's Woodford subcropping there on the high. You see the conglomerate sitting on it, so you get these debrites on high conformity. What you see is that if you look at this Wolfcamp section here, basically it's a thick wedge at a Delaware Basin up against the high, and it's absent on the Central Basin platform. So I think that does have flexural aspects to it. That's less clear in the Midland Basin side. But what's interesting, if you look at the subsequent subsidence in the Leonard through Ochoan, it looks like a more long wavelength subsidence phenomenon. Everything is going down, as you saw in those geohistory plots. So there's a change from, you know, kind of as we see for the Western Interior, we get these dynamic subsidence events. Don't ask me about the geodynamics. I don't know if I believe it for the Western Interior. And then we get these, then we get these things that look maybe more flexural. And you can see this unconformity and outcrop. This is south of High Rolls and the Sacramentos. You have this anticline of the Holder, the sort of ice house cycles being truncated by the Abo. And then in the Waco Mountains, you've got the Magdalena, which is lower Penn in age, being truncated underneath this middle Wolfcamp Powell conglomerate. And you see the synorogenic conglomerates developed on both with a variety of class types, including some basement classes. So you see this in the subsurface, broken record, insert here. So this is a seismic line over the Central Basin platform. You see these fault propagation folds, you see it being truncated under that, and then just kind of draping on top, and a big, thick section of mostly carbonates sitting on top of that. So I think there's something fundamental changing. If I just want to contrast with one arm basin, that's the Anadarko. It's probably that and the Paradox are two, I think, purely flexural arm basins of very different fills. This has a similar fill to what we saw for the Ardmore and the Arkoma basins. It has a kind of a deeper water Pennsylvanian with turbidites, et cetera. You got this granite wash coming off the Wichita uplift. But here, look at the age of this. This commences in Mississippian time. So very old. So these arm basins are going up and down at the same time. And to summarize that, we see that we've got this younging to the northeast in the Appalachian. We see this younging to the west with the Ouachita Marathon. And then most of these arm basins are kind of intermediate in age. They're basically Pennsylvanian through Permian. But then we've got this funny little area around the Arkoma and Hardiman basins, which are two flexural basins on either side of the Wichita uplift that start off really old. And I would, don't know, is the short answer. The long kind of question is, this is one of the most fundamental kind of tectonic elements of the Proterozoic is the South Oklahoma allocogen that got inverted. And so that's such a big fabric element, is that maybe that pops off early and is actually feeling this first indenter out here and activates that before the rest of these basins feel in some kind of more conventional laramide fashion. And don't ask me about the ochre, so that's mystery. And then finally, final thing, 2 slides on the antler. This is the most poorly understood of these, well, Ellesmerian actually is, but this, for what we're talking about, this is really poorly understood Middle Devonian through Mississippian foreland that's been interpreted. And the reason for that is that it's kind of seen a lot of pain. You had the severe front shown here in pink. You had the laramide deformation shown in purple. And then you had the basin and range shown in yellow. And so the only place that's really kind of clear of all this is up in Canada. And so I'm going to kind of focus on this Liard, which hasn't been hammered by all the subsequent deformation. And so if we look at the geohistories up in the Liard Basin, we see that we get this subsidence commencing in the Middle Devonian and it continues through most of the Mississippian. The site here at the flank of the Peace River Arch, it's first onlapping basement then, and it continues around the same time. And I think interestingly, if you look at the Williston Basin, the largest subsidence event there is Coeval. So another of these classic sag basins. And moreover, at least by the publications, the major movement on the only kind of real structure in the basin, the Ness and Anticline, is coeval with this. So we're even seeing some intrabasinal deformation reported in this Devonian, Middle Devonian, Mississippi event. And lastly, the Horn River shales, which you may have heard of, the very large shale gas resource in British Columbia and Northwest Territories, is deposited at the onset of this subsidence. And so this barely gets into the preserved foreland because the rest has been eaten away by the severe. But you see these Horn River shales, the Musquat or Park and Evie, and they're restricted to the 4 deep, and they're basically onlapping and overlapping and thinning the kind of equivalent carbonate platforms of the Cape River and Slave Point. And the X-Shaw, which is much more widespread, source rock in the basin that sources a lot of the conventional oils, thins tremendously once it comes out of this 4 deep. And so, same old, same old. So a lot of stuff here, but I'd just say in a sort of general sense, I think basin response is a potentially underutilized and useful constraint on the timing, magnitude, and location of orogenesis. I think it really complements sort of the more direct structural analyses, which of course are still really important, but sometimes are hard to do in these ancient systems. And I think this approach can even be extended to inform larger scale geodynamic models. And we start to pose some questions about these old plates and their impact times and their geometries. We also see these linkages at a plate scale, especially from plate margin to interior elements, whether they be sag basins such as the Michigan, Hudson's Bay, and Williston, and also the thick skin deformation that we see associated with the ancestral Rocky Mountains. And hopefully, while I think there's tremendous variability on the motifs here, there is such a strong control tectonic stratigraphy that we can start to leverage sort of for play element scale things. And I spent more of my time on source rocks, but reservoirs such as the Granite Wash, et cetera, are also really important. And that's my story, and I'm probably not sticking to it. So.